Namaste. Welcome back to Real-Time Digital Signal Processing course. Today we will discuss about Graphic Equalizer. So, we had seen the demo, but again we will be demoing after completing the theory. So, the previous class we saw that how to do echo cancellation and even generation in the previous class what we had seen the thing, why we have to cancel the echoes. So, if it is required as a hobby, you can generate the echoes, and if you are not want the echoes which are generated by different sources, so you can do the cancellation. So, today what we will see is the graphic equalizer. So, why do we need equalizers? So, we know that we use in home sound systems, vehicle sound systems also, in musical instruments, amplifiers and processors, even in studios and even live concerts, including our public address systems, and then you can go on listing where we will be using the equalizers. So, it is used to boost or cut certain parts of the audio frequency spectrum. So, which changes the way the original audio sounds. So, equalizers can be classified into 4 categories. One is tone control, the other one is graphic, so console and then parametric. So, it is the graphic equalizer is a tool for independently adjusting the gain of multiple frequency regions in an audio signal. So, the common graphic equalizer design can provide up to about 30 controls for manipulating the frequency response of each audio channel, and structurally a graphic equalizer is set of filters. So, if we are designing in the digital domain, each with a fixed center frequency and bandwidth. The only user control is the command gain what it is provided, or the amount of boost or cut in each frequency band, which is often controlled with vertical sliders. So, it is a very popular device for sound enhancement, although it is more restricted than a parametric equalizer. Digital music players such as those available in mobile phones, because most of us use the thing, usually have several preset settings for the graphic equalizer for different music styles such as pop, rock and then jazz. So, one can investigate what are the things you need it for your music players. So, continuing with the thing. So, this can be implemented using either a cascade of equalizing filters or a parallel bank of band pass filters. So, we have discussed about the filters. One of them you can consider in the cascade form or in the parallel form. Bands in the graphic equalizers are two common designs are octave and 1/3 octave graphic equalizers what we have it. So, an octave is a musical interval which is defined by doubling in frequency. So, octave graphic equalizer will have the ratio, that is we call it as R is equal to 2 between each band. So, in 1/3 octave design, so each octave contains 3 bands, which implies that R3 is equal to 2, or R is given as 1.26. So, starting at 1000 hertz, that is 1 kilohertz, an octave spacing would have geometric mean frequencies at 2 kilohertz, 4 kilohertz, 8 and so on. And in 1/3 octave spacing would have filters centered at 1260 hertz, 1587 hertz, 2000 hertz and etc. To call you back, we generated a musical note Saregama Nisa. So, if you remember that complete thing what we call it as 1 octave. So, we started with the base frequency 240 hertz there, and we went up to 480 hertz, and different bass what you can select. I think music lovers will be knowing C, C sharp and whatever their tone is going to be, you can set at it and then you can go on adjusting your frequencies. So, the number of bands is going to be determined by the spacing and the requirement to cover the entire audible spectrum what it is going to be considered. So, what we call it as octave graphic equalizers usually have 10 bands ranging from about 31 hertz at the lowest to 16 kilohertz at the highest. So, the third octave design usually have 30 bands ranging from 25 hertz to 20 kilohertz. So, you will be seeing that how the difference of frequencies or bands what you have to select in your design part of it. So, to show that octave frequency bands, you can go to net and then you can see. So, search for the thing, you will be getting it. Here whatever preferred octave frequency bands according to the ISO standard what it has been listed. So, you will be seeing that lower frequency f1 hertz is 22 to 11,360, that is 11.36 kilohertz what it is going. So, in the geometric mean frequency, that is FC, which is the cutoff frequency, center frequency what we call it. So, which varies between 31.5 hertz to 16 kilohertz in this, and the upper frequency one can have is from 44 hertz to 22.72 kilohertz. So, this is the table shows, and then that is for complete 1 octave. And if you say see for 1/3 octave frequency bands, the ISO standard is given as this. So, what you have is f1 and then you will be seeing little variation with the thing, it varies from 22.4 to 562 what you can see it, and your center frequency is somewhere from 25 hertz to 630 hertz what it goes. So, what it says is bold font represents the center frequencies in this case. So, because we said it is 30 bands what it has, so this is represented in one column. So, in the next column you will be seeing the upper frequencies what it has it, and then from the 500 and this thing 62 it goes from to 708, and then you will be seeing up to 17.78 kilohertz. So, totally you have 30 bands in it, and these are the center frequencies what you will be providing for them, and these are the upper frequencies. So, for these frequencies these are the center and these are the upper frequency, and for this set you will be seeing this as the center frequency and then upper frequency. So, this is how synthetically you can generate your equalizers. So, how to go about designing it? So, in this case first we will consider the cascade part of it. So, if you want you can go to the theory and then see how the design is going to be done. In this case we will consider we are going to give this is the input audio what it is going to be, and this is the overall G0 gain for the audio what we can give it, and then for each band here it is 3 band or M bands what you are going to decide. It can be 1 octave or 1/3 octave what you can select. So, if it is 1 octave it is 10 equalizers what you will have it, and 1/3 you know that 30 what you need it equalizers basically, and for each one the gains can be varying from G1, G2 to Gm basically. So, what it says is M is varying between 1 to M is the filter index, receives as input the output of the previous band filter, and finally, the last band we call it as Hm of Z produces the equalized output signal. So, this is what how you provide octave basically. So, the band filters are Biquad filters. I think it should be something is ringing in your mind. So, when we use the biquad basically in IR filters. So, as you will be seeing that it is a biquad section what we have chosen. This is the input and this is plus and minus, this is the feed backward path and this is the feed forward path. So, if you want to have a B0, you can give the thing, most of the time it is going to be 1, that is why it has been removed, and then this is a Bi of m, because number of stages is going B1 comma m will be varying between 1 to capital M. So, so many stages what you can do concatenation basically, that is cascading what you can do. This is a B2 coefficient comma m, and this is A2 comma m, and then this is A1 comma m. Okay. So, you will be seeing this is our output after adding it, and then because we know that our feedback coefficients are negative, that is the reason why what you have put it as negative in this, and these two getting added, and then after that it is going to be subtracted. So, if you remember the equation, so what we have it is, I will write here, y of n is equal to b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 and minus y1 of n minus 1 minus y2 of n minus 2. Sorry, this is A1 and this is A2. A2 into y of n minus 1, y of n minus 2. So, this is the equation what we have it for the biquad section. So, A1 and A2 are the coefficients for the poles basically, and then B0, B1, B2 are the zeros. So, this is what our biquad equation, so which is written in this way, and then z minus 1 will be in the z domain, the delay which is provided for x and then our y what we see it. Right. So, what we can do is one filter is used for per band what it says. So, that m is equal to 10 such filters are needed for a standard 10 octave graphic equalizer. So, each modified filter which is named with Archimedes band filter has its own linear gain GM what we call it, and center frequency FC comma m for each this thing what it is defined. So, now coming to the thing, first it is necessary to select the center frequencies FC comma m which are here set to the recommended octave center frequencies what it is given with previous slide what you have seen the thing, that is these are the center frequencies, mean frequencies what we have it for the 10 band, same thing what it is going to be considered here in the case. So, next one is 62.5 and then 125 hertz and then so on up to 16 kilohertz. So, 10 band center frequencies what it has been chosen. So, now we will see what are the magnitude response of an octave graphic equalizer. So, you will be seeing that the thick line what it shows is the cascade structure. So, you are seeing the this is the input and this is the output, and these colored curves what it shows is 2 shelving and 8 band filters what it has been considered here. So, you will be seeing that this is a low pass filter, after that what you have is the band pass filters. So, each one represents the center frequency of each one of them. So, we have it 1, 2, 3, 4, 5, 6, 7, 8, 9 and then 10. Okay. So, you have what is it shows is 8 band filter with what we say Q is 1.41 of the cascade structure. So, what it says is red circles command gains all at 10 dB, as we can see that all of them are at 10 dB, and this is the frequency in hertz what we are going. So, that is whatever in the previous one we had said that 31.5, 62.50. So, you will be seeing they are the center frequencies what it has been chosen along the x axis, and y axis will give us the magnitude of it. So, the cascaded what it shows in the thick line here. Now, how we can design the same thing in parallel, that is what this figure shows. So, we will be having the overall gain G naught here, and then each one will have its own impulse response H1 of Z, and they will be this thing multiplied with their gains in parallel, and then you will be seeing that each one is getting added, and then what we will be getting get out. So, what it says is here all band pass filters receive the same input signal, and the output is obtained as a sum of individual filter outputs, that they are weighted by the command gains. So, one has to think now whether we want to have the cascade graphic equalizer as it is shown here, or the parallel. Can you think of it, because we have seen even in IR filter design, we said for our hardware, because we are using DSP processor, or if you want to implement in FPGA. So, we said that multiplication overflow is taken care of, whereas the addition we are going to have a overflow in it. So, we have to check every time if there is output is overflowing, then we have to scale them, and then we will be taking care of all the overflows. So, it is better to go with cascade section in hardware than the parallel structure, although we have both the things. So, if you are able to take care of whatever the overflow which is going to come from the addition in the input itself, then we can use the parallel section, because we know that this is much faster compared to our cascade section. What I will put it as, this is parallelism what I can use it here. There I have to use the pipelining, in between I have to put a what I will say is a buffer basically, or a delay unit, so that each one will be pipeline structure what I can use. So, you will be recollecting your pipelining and parallelism what we used in the theory here, and then can go for implementation of it. So, the next is we will take up as an example, one can design a 3-band equalizer. So, it depends on some of the books gives that we can go with the 3-band is enough. That is what you will be having. Tone control was designed with frequencies of, that is 200 hertz, that is low shelf what you will be considering it, and 1 kilohertz mid peak, and then here Q is taken as equal to 1, and 5 kilohertz what it says is this is the high shelf. So, with this also you can design your graphic equalizer. So, you will be seeing that what is it. So, the dB what it is shown from here, that is minus 12 to 12 dB, what you will be selecting it on different spaces, and then this is your FC is your cutoff frequency, and then your you call it as low filter shelving what you will have it, and here cutoff frequency FC gain G in dB what you will be providing it to the system. And then the next one, this is a low pass filter as we know, and here it is a band pass filter, that is middle frequency what we can call it as peak, that is cutoff frequency FC bandwidth FD gain G in dB what you will be taking it. So, this is our cutoff frequency, and this is the frequency range FD, that is pass band region what you will be selecting it. And the next one, so on what you can design, and next is the your this thing multiple middle frequencies what you can see, and then their peak, and here your cutoff frequency is what you will be specifying with their gain as well as your band pass the structure what it is shown here FD. And in the last what you will have is as a high pass filter. So, which is HF, which is given with cutoff frequency as usual FC, and it says high filter shelving the last stage, and cutoff frequency is FC and its gain is G in dB what it is given. So, whatever dB you want to select you can select them, and Yn is your output. So, how we can design the thing? All of us know that audio file is given in the time domain. So, x of t is our input, which is coming from the, it can be from the mic or audio system. So, then we have to convert it into digital domain, that is we will be using ADC. Depending on number of bits what we wanted, we can select our ADC, and after converting it into digital domain we will be getting x of n as our input, which will be passing it through the equalizer, and y of n is our output. Then what is it? So, if I want to convert this back to audio that is our time domain, then I have to use the DAC, then y of t will be the output. But I do not want to use this ADC and DAC, but I want to see that whatever I have stored it, whether I can provide the equalizing filters designed for this equalizer filter 1, 2 and then M, if it is whatever band you will be selecting it. So, that is what the cascade section what you are seeing it, which goes into your equalizer. So, now you will be seeing that in the market a 3-band equalizer is shown this way. So, what is it? You have a low frequency knob which you can adjust it, and then this is the mid frequency what you have it, or middle one. So, different one what you can select here, one of it low or high, whatever FD bandwidth what you want to have it, and this is the high frequency what you will be selecting it. So, you are seeing this is our low pass filter, and this is what it is shown is the inverse of it. So, that is band stop what you are seeing it, and whatever frequencies you want to pass it. So, you can put it as a band pass filter, and then the other one is the high frequency filter what you are having it, and some of the frequencies how you can adjust it what it is shown in this blue color. So, this is the commercial which I have taken it from the net, and then I am showing you how it can be designed. So, this is completes our adaptive filter and their applications, filter applications what we have considered for band pass filter, low pass filter and high pass filter, how it can be used in scrambling, echo generation and cancelling, and then in the equalizers. So, in the next class we will be discussing about the speech coding techniques that is available in the literature, and we will be considering one of the example how we can design both in MATLAB and then in Code Composer Studio. So, thank you. So, happy learning for this material, and then we will meet in the next class. Thank you.